Hi everyone. When Coulomb was originally investigating the electric force and the formula for it, he was really inspired by Newton's law of gravity, and we've made this point in the past. The interesting thing about the comparison is that the electric force is vastly stronger than the gravitational force. I mean, we're talking about on the order of 10 to the 20th power difference between the two forces. You know, that's 1 followed by 20 zeros. I guess that would be a billion, 100 billion, billion, something like that. And so it really begs the question, where the heck is the electric force? I mean, every time I get out of bed, I have to overcome the force of gravity. Why don't I have to overcome the force, this electric force that's supposedly so strong? And the reason is because everything we deal with is electrically neutral. And unlike the gravitational force, which only has one type of charge, quote unquote, one type of mass, the electric charge has two. You've got pluses and you have minuses. And those pluses and minuses can get together, and basically what happens is, because a plus and a minus are typically attracted to one another, they tend to clump together. And this picture here represents the simplest possible system between a plus and a minus. This is called a dipole because there's basically two elemental charges in place here. And this dipole is really what every single atom is made of. You know, fundamentally, atoms are made of electrons, protons, neutrons, and those protons, neutrons are composed of quarks, et cetera, as you go down the chain. Now, each one of these fundamental particles are charged, plus, minus, whatever it is. The only exception is the neutrino. But because they combine together in the atom basically locks these charges together so that the external influence is minimized, because far away from the charge you look and you see effectively the pluses and minuses counterbalance, and there's no effective electric charge far away. And so in a sense, the electric force is shackled by its own strength. And so we only see the electric force indirectly through all the other mechanical forces that I've been talking about. Tension, the electric force, all sorts of friction, you know, all the everyday forces that we experience, with the exception of gravity, are fundamentally electrical through the interaction of atoms. And that really explains why we do not see the electric force as much as we do the gravitational force. Now this system here, this dipole, basically you define the magnitude of that dipole via this equation here. P represents the dipole strength. It's just the charge multiplied by the distance between the charges. The thing about a dipole, and remember this is the most common form of electric configuration that we'll deal with. It's the simplest form, really. Is that each one of those charges, if you place it in an electric field, say the electric field is going this way, the positive charge will be repelled from a positive electric field, the negative charge will be attracted. And what that ends up doing is basically this gets pushed up, this gets pushed down, and you get a twist, a torque. And so every dipole in the presence of an electric field doesn't experience a force, a net force, it experiences a torque, which will have a tendency to twist it. And this is the magnitude of that torque. Basically, it's the dipole, the magnitude of the dipole times the electric field creating that torque, and then the sine of the angle between the two. And that sine guarantees that once the dipole twists, basically it will experience no net force after that. So basically the dipole will align with the electric field. It'll twist until it's lined up. And then it won't twist anymore, because basically the plus charge has gotten as far away as it can, the minus charge has gotten as close as it can, and they don't twist anymore. The one last thing I forgot to mention is that this formula, although there is a way to derive it, I'm not going to go through that derivation. That's just to show you what the potential is far away from a dipole. And you can see that it varies with the inverse square of the distance, which means that the force actually varies with the inverse cube of the distance, which is why it's much weaker than the corresponding gravitational force.